A little while ago, I made a video about sizing the cable between solar panels and a charge controller. In that video, the method I used was completely safe, but after reviewing it more carefully, I realized it can sometimes lead people to choose a larger and more expensive cable than they actually need. So in this video, I want to clear that up and walk you through a better way to calculate voltage drop for solar panel cables. The goal is simple: keep the system safe while avoiding unnecessary cable costs. Before we jump into the numbers, let's quickly review why voltage drop matters. Every wire has resistance. As electricity travels through a cable, some energy is lost because of that resistance. The longer the cable run, the greater the resistance becomes. This loss does not reduce the current flowing through the wire. Instead, it shows up as a reduction in voltage. In other words, the voltage available at the charge controller will be lower than the voltage leaving the solar panels. That is why solar designers try to keep voltage drop within reasonable limits. A common target is 3% or less. For example, imagine a solar array operating at 100 volts. A 3% voltage drop means you could lose about 3 volts in the cable run. That would leave roughly 97 volts reaching the charge controller. If the current flowing through the cable is 10 amps and the voltage loss is 3 volts, the power loss would be 30 watts. In most off-grid systems, the cable between the solar panels and the MPPT charge controller is usually the longest cable run in the entire system. Because of that, it is often the place where voltage drop calculations matter the most. Let's go through a real example. We will use two 200-watt solar panels connected in series. Here are the panel specifications. The first step is making sure the cable can safely handle the maximum current that could flow through it. For that, we start with the panel's short circuit current, which is 8.91 amps. Next, we multiply that value by 1.56. That gives us a maximum design current of 13.9 amps. The 1.56 factor comes from two separate safety margins combined together. One accounts for continuous operation, and the other accounts for higher operating temperatures when the cable is exposed to direct sunlight. Using that maximum current value, a 14-gauge cable, which is approximately 2.5 square millimeters, is already large enough to safely carry the current. So, if the cable run is short, that wire size would generally be acceptable. But in our example, the cable run is much longer, which means we also need to calculate voltage drop before choosing the final cable size. To do that, we first need a few important values. We need the solar string voltage and the cable length. Since we are connecting two panels in series, the operating voltage of each panel is added together. Each panel has a maximum power voltage of 23.75 volts. Multiply that by two panels, and the string voltage becomes 47.5 volts. For this example, the solar panels are located 50 feet away from the charge controller, which is about 15 meters. That distance is the one-way cable length. Most voltage drop calculators automatically account for the full round-trip distance internally. Now let's compare the old calculation method with the updated method and see how much difference it makes. In the older method, I used the full design current of 13.9 amps for the voltage drop calculation. So, for the calculator, we enter a system voltage of 47.5 volts, a one-way cable length of 50 feet, and a current value of 13.9 amps. With those numbers entered, we adjust the cable size until the voltage drop stays below our target of 3%. The result is an 8-gauge solar cable, which is roughly 10 square millimeters. Using that cable size, the voltage drop comes out to approximately 2.28%, which is comfortably below our 3% limit. From a technical standpoint, there is nothing unsafe about this design. The system works perfectly fine. The downside is cost. For a 50-foot run, an 8-gauge PV cable can cost around $77. Now let's look at the updated calculation method. The key difference is the current value used for voltage drop calculations. Instead of multiplying the short circuit current by 1.56, we multiply it by 1.25. For this panel, that gives us a current value of 11.14 amps. Why the change? Because when calculating voltage drop, we only need to account for expected operating conditions. The additional temperature-related safety factor used for conductor protection does not need to be applied a second time during the voltage drop calculation. So we keep the same voltage of 47.5 volts. We keep the same 50-foot cable length. The only thing that changes is the current, which is now 11.14 amps. When we run those numbers through the calculator, the required cable size drops from 8 gauge to 10 gauge, which is approximately 6 square millimeters. Even with the smaller cable, the voltage drop remains within the recommended limit. And this is where the savings start to appear. A 10-gauge PV cable for the same distance may cost around $50 instead of $77. That means correcting the voltage drop calculation can save roughly $25 on a single cable run while still maintaining a safe installation. Now, before anyone rushes out and starts choosing smaller wire, there is one very important step left. Just because a voltage drop calculator recommends a cable size does not automatically mean that cable can safely carry the maximum current. That final verification is something every installer should do before making a decision. And that safety check can completely change the answer in certain high-voltage solar systems. So let's perform that final safety check. Remember the maximum design current we calculated earlier? That value was 13.9 amps. Now we need to confirm that our selected 10-gauge cable can safely handle that current. Looking at a standard ampacity chart, a 10-gauge PV cable is rated for approximately 40 amps, which is well above our 13.9 amp requirement. That means the cable passes the current carrying test and can be used safely in this example. This extra verification step is important because voltage drop calculations do not tell the whole story. Let me show you why. Imagine a much higher voltage solar installation. Instead of 47.5 volts, let's say the solar string is operating at 450 volts DC and carrying 35 amps. Because the voltage is much higher, the percentage voltage drop becomes much smaller for the same cable length. As a result, a voltage drop calculator might suggest a surprisingly small cable. For example, the calculator could indicate that a 14-gauge cable, or roughly 2.5 square millimeters, produces a voltage drop of only about 2.42%. At first glance, that sounds great. The voltage drop is below 3%, so everything appears fine. But when we check the cable's current rating, we find a problem. A 14-gauge cable is typically rated for around 25 amps, while our system requires 35 amps. So even though the voltage drop calculation looks acceptable, the cable itself is not capable of safely carrying the required current. That is why voltage drop should never be the only factor used when selecting cable size. The cable must satisfy both requirements. First, it must keep voltage drop within acceptable limits. Second, it must safely carry the maximum expected current. In this example, we would need to increase the cable size to 10 gauge, which is rated for about 40 amps, and can safely handle the load. Before we finish, let's talk about safety. The cable between the solar panels and the MPPT charge controller is often the highest voltage section of a small off-grid solar system. When multiple panels are connected in series, it is very easy to exceed 50 volts DC, and at those voltage levels, electric shock hazards become much more serious. DC arcs can also be extremely dangerous because they are harder to extinguish than AC arcs. To reduce risk, follow a safe connection sequence. Start by connecting the battery to the MPPT charge controller and complete any required setup or programming. Next, connect the PV cable to the charge controller, but do not connect the solar panels yet. After that, connect the solar panels and use a multimeter to verify both voltage and polarity. Once everything has been confirmed, switch on the PV disconnect and bring the solar array online. Also, always stay within the maximum PV input voltage and maximum PV input current limits specified by the charge controller manufacturer. And whenever possible, avoid working on energized solar strings. So, to summarize, the older approach used the short-circuit current multiplied by 1.56 for both cable ampacity calculations and voltage drop calculations. The updated approach still uses 1.56 when checking the maximum current carrying requirement of the cable. However, for voltage drop calculations, we use the short-circuit current multiplied by 1.25. In many systems, that change allows you to select a smaller and less expensive PV cable while still maintaining proper safety margins. The result is a design that remains safe, meets electrical requirements, and can reduce overall installation cost. Let me know in the comments what size PV cable you're using in your solar system. Thanks for watching, and I'll see you in the next one.